WDM and TDM are both methods to combine multiple signals over a single communication medium. However, the technologies that they're both based on are completely different. If you want to find out more, stick around and we'll check it out. As the names already describe, wavelength division multiplexing and time division multiplexing both are multiplexing technologies. But that is pretty much where the similarities end. Let me explain. First of all, WDM is a multiplexing technology in the optical domain. And how that works is we've got these different signals that come along with different wavelengths. And those wavelengths are then combined and separated on either side of the link, for example by using optical filters. But that is basically where the name comes from, wavelength division, as in the individual signals are divided from each other by using different wavelengths. But the good thing is that the different wavelengths are actually being transmitted at the same time, so in parallel. And that also means that if we were to add more wavelengths to the setup, we would actually be increasing the overall bandwidth of that link. And the limit basically is the number of available different wavelengths, in other words, transceivers. Now TDM, on the other hand, is a multiplexing technology that is mainly used in the electrical domain. And it combines different signals into a data stream by assigning different time slots. And how that works is we've got these different signals, and each of these signals is allocated a short time slot within a periodic sequence to transmit the data. In other words, you can imagine this string of boxes or time slots is continuously moving from left to right. But that once again is where the name comes from, so a time division, as in the individual signals are divided from each other by using different time slots. Now there are two different types of TDM. First, we've got the synchronous TDM, where these different time slots are fixed and allocated to the individual signals regardless of their bandwidth requirements. So even if one signal isn't transmitting anything, it still gets that time slot. And on the other side, we've got the asynchronous, also called statistical TDM, where the time slots are actually allocated dynamically to the individual signals depending on their bandwidth requirement. Now, unlike with WDM, TDM does not add to the overall bandwidth of that link. On the contrary, it is actually sharing that bandwidth between the different signals. So what are the main use cases of WDM and TDM in telecommunication networks? Well, for WDM, it basically is everywhere where the fiber capacity of the existing fiber is at its limit. So in other words, instead of having to deploy additional fiber, you can use WDM to maximize the capacity of the existing fiber. And that means that it can be used for metro and core networks, it can be used for data center interconnect, it can also be used for X-hole fiber links, just to name a few of the possible applications. Now for TDM, well, the main application in telecommunication networks is for FTTH, so fiber to the home applications, and that is simply because it is very much more cost effective than an equivalent WDM setup would be. But that doesn't mean that WDM isn't used in FTTH applications. On the contrary, for one, the different PON generations use different wavelengths in the WDM grid simply so that they can be used in parallel. But in addition to that, we've also got the NG-PON standard, so the next generation PON standard, and that uses a combination of TDM and WDM, which is then called TWDM. So, I hope you learned something today and that you enjoyed this video. If so, please leave a comment. And of course, remember to follow our channel so you get your regular dose of brain snack. Until next time, bye bye.